Welcome back, friends. So we were continuing discussing about S matrix and how to calculate process, simple process like scattering, what we took and the entire idea of non-relativistic quantum mechanics will not work. So the main ingredient how to make scattering process work in relativistic sense would be, first of all, to modify the equation of motion, essentially to modify the equation of motion, okay, and do not treat the potential as some sort of a local meaning some sort of a step potential or something localized in space and everything essentially, but instead modify it in terms of interaction, modify it. So what we are trying to do is essentially write down the full Lagrangian, fully consistent relativistic Lagrangian, okay, and then derive the equations of motion and then derive the equations of motion. So we have seen that the equations of motion for the Dirac for the example we have written the QED Lagrangian, and what we have seen, the equations of motion get modified in the presence of the interactions. Say for example the Dirac wave equation gets modified into this particular fashion and the electromagnetic wave equation of motion gets modified into this fashion, okay. So the electromagnetic equation of motion for free particles is nothing but this, whereas free in the presence of forces this becomes this. This is well known because we studied it in our classical electrodynamics. So the electromagnetic Maxwell's part will become this, and the free and the Dirac part becomes this, the Dirac part becomes this, okay. Now this is the technology we are going to use. We are going to use something called propagator technology, propagator theory, to calculate the scattering cross sections. We are not going to use the Laguerre way. It consists of two steps. First, writing down this particular thing in terms of fully relativistic form, fully consistent Lorentz covariant form of the Lagrangian, and deriving the equations of motion. And we can still do not have to go to the full quantum field theory, we do not have to go to the full quantum theory technology. We can still use Dirac wave functions and electromagnetic wave functions, free particle wave functions. And with the way we implement perturbation theory is that we treat this perturbation theory as exactly like what we do in quantum mechanics. We treat the original wave functions to be free, or the original wave functions to be free, but now because the interactions, so we multiply the interaction. Now what we can do is we can multiply, because we are writing everything in terms of wave functions, the interaction is also written in terms of wave functions, okay. It is written in terms of wave functions. It is no longer a step or something 1 by r potential or something. Instead it is written as a multiplication of wave function. The interaction is written as multiplication of wave functions which are all considered free, okay, which are all considered free. This is the point essentially, that we are not solving the full equations of motion in the presence of interactions. Instead we are just multiplying. The interaction is multiplication of free particle wave functions. And now we define in and out states. In and out states technically in quantum field theory they become something, t goes to infinity, they become something called asymptotic states, okay. We do not have to worry about it. Right now we just take them to be as free particle states. They come in at the vertex, at the vertex you multiply these three wave functions, the outgoing wave function, the incoming wave function, and the third wave function which we multiply is a propagator wave function. So what is a propagator wave function? The propagator wave function is the mediator between the two particles. So the process we are considering here is a simple process which is E minus is scattering to E minus E minus. It is electron scattering another electron. Okay. We are not writing the presence of the potential in the presence of so we are not putting the classical potential generated by one of the electrons and then doing it essentially. We are actually taking both the electrons to be scattering with each other, and then we wrote that there is a wave function which which is propagated from one vertex to another vertex, which is propagated from one vertex to another vertex, which we call as propagator wave function. And what does this propagator wave function do? The propagator wave function takes is the solution of the wave equation in the presence of a delta function source. So the interaction is treated as a delta function source, and we will come to that why. There is a good reason why we do that. And then you solve the wave equation, and that gives you the propagator solution. You put it back into this calculation and you multiply these wave functions along with the propagator, taking into consideration consistency of Lorentz invariance and unitarity and everything. Essentially that is the reason why the S matrix becomes because the S matrix is unitary. So this resultant amplitude is the scattering cross section of E minus E minus SLA, and this gives you consistent results together with how we treat antiparticles, okay. Then this gives you completely consistent results in relativistic quantum mechanics. And see, we are not using any field theory approach as of now. This is good. We do not need to use any complete quantum field theory techniques, okay. This is good as long as we stick to tree level interactions, okay, and as long as we stick to tree level diagrams or first order in perturbation theory. So first order in perturbation theory means that you consider only two vertices of interactions, good. So now so this is the reason why this is how we define an interaction as an S matrix, and how to do calculations which are consistent with relativistic quantum mechanics essentially, and which gives you correct answer. So what are propagator methods? Propagator methods are already known to us, but we call it in a different way, okay. We call it in a different way okay. So how to derive a propagator, okay, what is propagator? Now these propagator methods are already known, you do not need to know relativity, and just we use classical field theory in electromagnetic theory and everything, okay. These methods are already known, okay. These are instead called as Green's functions methods. Okay, because we write it in terms of momentum space, we call them as propagator methods, but these are already known in space time. If you write it in ordinary x and t plane, essentially these are your Green's function methods, but in momentum space we write them as propagators essentially, because we try to calculate everything in terms of momentum space. So to give you an example, let us start with a very simple example, which is non-relativistic with an equation which you already know, all of you essentially. Okay, like I said, these are Green's functions methods are already known. So they are based on the general principle that if you have a single particle source on Huygens principle essentially. So, if you have a single source, okay, if you have a single source and then this wave front travels, the wave front travels in this particular fashion and each one propagates further at the front of the wave front essentially, and so you have another wave front essentially. Okay, this is does not coming very symmetrically, but anyway, okay, and so this point becomes like this point becomes like this point. What you can do is you can take these points perpendicular to the wave front essentially, this is like the Huygens principle essentially in classical optics. And keep drawing these wave fronts essentially. This is how it tells how a wave propagates in time, how a wave propagates. So, how a wave propagates in time. So, in general, if you have a wave function at some time t x and t and you want to find the wave function, okay, at a later time, t prime greater than t, we want to find its wave function. So, what you will write it down as psi x prime t prime is equal to I t cube of x g of x prime t prime g of x t psi of x t. Now, here this is completely non-relativistic. The example we are taking is non-relativistic example. Now, this is how you see, and this g, how do you find this g? This g is nothing but your Green's function essentially, nothing but your Green's function. Okay. Now, let us look at the case of okay, let us look at the case now in general. Okay, let us look at the wave function essentially psi. Okay, let us look at the wave function psi. Okay, and before finding out okay, how do you find g and everything essentially, let us look at the wave function psi, and then we will see how to calculate g. So, the general this is I think which you already know, but I am repeating this. This is something you know in time dependent perturbation theory, but in also in non-relativistic quantum mechanics. Let us just say that, let us start with solution such that, so psi is a solution of a Hamiltonian like in ordinary quantum mechanics, h psi is equal to E psi. So, at psi of x0 t0, and let us imagine that there is a potential at V of x1 t1. At x1 t1 there is a potential which acts at an infinitesimal time. It acts at a very small time essentially, it acts at a very small time Okay, this is the potential which acts on psi at x1 t1. At an infinitesimal time. In that case, okay, this potential will act as a source. Now you will see why this entire set of arguments is to tell you why I can use a delta function source to solve the propagatory equation. Okay, at the end of the day you will see that. Now at time t1 I can write the equation as I del by del t1 minus h0 psi of x1 t1 is equal to v of x1 t1 psi of x1 t1 delta t1. This is a very small period of time, in the sense around t1. Okay, it is an infinitesimal time around t1 in which this potential is acting on psi. Now what you can do is, for this wave function, okay, you want to solve this wave function, essentially you want to solve this wave function. So you want to solve for, so in general what you can do, write delta psi x1 t1 is equal to minus I v x1 t1 phi x1 t1 delta t1 and this is equivalent to delta psi x prime t prime. Now here, okay, let us understand this particular thing. Now phi is a free particle wave function. I am introducing free particle wave function here and assuming, I am using perturbation theory, I am assuming free particle wave function here. Now at another time x prime t prime, we have delta psi So what I did here is, from moving away from propagating from x1 t1 at this small point, essentially at x1 t1 the interaction acts, after x1 t1 at a point x prime t prime I can write another propagator, as another wave this thing which tells you how to take to this one. So if I write the space time diagram, okay, you have where the interaction is acting here and this is moving away, again x prime t prime, essentially this is moving away. So this is x prime t prime to x of t. So this is the wave function in which xnt is your point, essentially x prime t prime is the original point, essentially it is moving to x prime t prime, where at x prime t prime, which is slightly away from x1 t1, okay, I should not put this, okay, it is slightly away at x1 t1, there is a small interaction, okay, which is playing at that particular point, which is a very infinitesimal point, okay, whereas this entire thing is a free particle propagation, essentially, which is a free particle propagation. So the particle is travelling in this particular fashion, okay. Now to be more accurate, let me exploit in a much more detail. So at xt I start with psi of xt, free particle. At this one there is x1 t1, it is scattered by a potential, and now I go to x prime t prime. Now let me erase x prime t prime here, let me not make this one, essentially at x time t prime. So this is being scattered at a particular so this is being scattered at x1 t1 by a potential which is infinitesimal, and this goes on to say, and then it goes to x prime t prime and so on, so essentially. So you have in general another propagator, okay, another propagator which is coming in at this particular thing. So this can happen in a series of ways, essentially. So you have in general g of x prime to x is equal to g0 x prime to x, which is a free particle thing, plus integral g0 g prime x x0 b of x1 g of x1 x and so on. So you can write this, you can introduce as many scatterings as possible if you go into higher order perturbation theory, essentially. So what you have is a free Green's function, the Green's function which is free, which is does not touch anything, times a small part of the Green's function which gets modified in the presence of v of x1, essentially v of x1. Now this turns out that you can actually show that the Green's function is nothing but sum of all the propagators, essentially, okay. There are a sum of all the wave functions, essentially sum of the solutions of the differential operator. The Green's function is the solution of the free delta function, okay, source of the differential operator of all the wave functions of the Laplacian operator, okay, it is a solution of the Laplacian operator. Now what we are considering, the potential we are considering is a non-relativistic potential in this particular case. I do not know, can I maybe I will repeat it in a couple of minutes, essentially, okay. Again just tells you that what we are applying is nothing but the Green's functions methods, which you already know in ordinary quantum mechanics, essentially, or in electromagnetic theory and so on. So it is the same thing, but we are applying it to quantum mechanics. It just tells you how the wave function psi of x prime t prime psi of xt propagates in time, and the kernel which takes psi of xt to psi of x prime t prime is nothing but your Green's function. In the presence of interactions, in the presence of interactions we introduce, so in like in time independent perturbation theory, we introduce interactions at a very small periods of time, delta t1, delta t2, so on. So essentially at that particular point the Green's function is modified with another g1, essentially the g gets modified and the total g is a free particle g0, essentially the free particle g0 and plus so on, so essentially with a E function with every input of the interaction at x1, x2 and so on, so essentially. Okay. Now this is what we have seen, this is a free particle thing, and this you can revise and do it. Okay, this is just this is a formalism, and but a more important point is that the Green's function now depending upon Hamiltonian, if the Hamiltonian is simple, essentially let us take the Laplacian Hamiltonian. We will see in the next lecture that in for the Laplacian Hamiltonian the Green's and we can show it for every Hamiltonian, the Green's function is with a delta function source. So this is equivalent to taking it into a delta function source, okay. And so what, because we are putting it an infinital point, essentially you are putting it an infinital point, and what you will see is the solutions of the Laplacian operator, the eigenvalues, the entire eigenvalues are nothing but the Green's function of the full solution with a delta function source are sum of all your eigenvalues, essentially of all your eigenvalues. So this is the basic idea of solving for the Green's function, okay. And we will see the statement I made in the next lecture, essentially that if you put in delta for the non-relativistic Green's function, which we will do for the next lecture for the Schrodinger equation, and what you will see is that the full Green's function is nothing but the solution of the sum of all the eigenvalues, essentially. I do not want to start now because it will take up more time, essentially. Okay, I will stop here and then we will continue in the next lecture. Okay, thank you very much, essentially.